Hello, this is a different kind of video. Instead of talking about something I'm doing in class, this is more of a contest problem. This was given to me by Professor Bogdan Suceava at Cal State Fullerton. He was basically trying to keep me from getting too bored during a meeting. And so he gave me this to work on, and I thought it was a fun enough problem that somebody might want to play with it. So we'll read the problem, and then maybe you can pause and try it yourself. So in this problem, we're trying to find all positive integers x, such that when you add x to the floor of its square root function, you get a perfect square. So for those of you who may not have seen this before, when we write down the floor function, so we use these, looks like a bracket, but it's missing the top. Some people actually use the top side too when they write it, but I think this notation is becoming more common. So this is going, for any real number, a is going to tell you the largest integer which is less than or equal to a. So this is the largest integer less than or equal to a. So if a is an integer, then the floor will just be a. So if we were trying to graph this, let's put 1 here. So between 0 and 1, well, the smallest integer, which is less than or equal to any number between 0 and 1, will just be 0. So it just floats around here at 0 for a while. But when you get up to 1, well, now it's going to take a big little leap. Big little leap. Yeah. So where's it going to jump up to? Well, it'll jump up to 1 because the largest integer less than or equal to 1 is 1. So it jumps up there. And then you head over to 2, and on its way to 2, of course, it's just going to stay at the same height 1 all the time. But then when you get to 2, it's going to make another jump, this time up to 2. Okay, so you get this nice step function. And this basically allows you to drop a remainder. So if, for example, I was looking at 3.1415 and I took the floor function, this would end up being 3. Now, if you're looking at negative numbers, which is not really the subject of this problem, but it's probably worth just pointing out, then it doesn't quite have the same effect as dropping the decimal. Right? So, for example, if we were looking at the floor of negative 2.318, so now I need the largest integer which is less than or equal to this. That would actually be negative 3. So it works a little bit differently with negative numbers. Okay, but for this problem, we don't really need to worry about the negatives, because again, we're only looking for positive integer x's, because we're going to be taking a square root. So one thing you quickly see here is that as x grows, right, the floor function is going to grow with it. Maybe not very quickly, but it will, eventually grow. And of course, if x is growing at the same, obviously if you're making, say, x greater than y, then x plus y, or rather x plus the floor of root x, is going to be greater than y plus the floor of root y, which tells you that this function here is an increasing function. And that's going to be very useful, because if we're trying to show that this number is a perfect square, well, kind of think about it backward. Imagine we had some perfect square. We have some n squared, which was equal to x plus the floor of root x. You might ask, well, is there another way for the same n squared, right, the same perfect square, to write it as, some say, y plus floor of root y? And the answer has to be no, because we have an increasing function. So one of these two, right, is going to be bigger than the other. So say, for example, we knew that the y was greater than the x. Then we would know that y plus the floor of root y is going to be greater than x plus the floor of root x, and so it can't equal n squared also. So if we have a solution to such an equation, we will only have one solution. Okay, so why don't we record that? So the equation n squared equals x plus the floor of root x has at most one solution for each n. All right. Now, what's the smallest n squared we could have? Of course, that would be 1 squared, right, or 1. And we know that, well, already if we start with 1 plus the floor of root 1, this is already equal to 2, which is greater than 1, or 1 squared. And so that tells us that when n is equal to 1, this equation won't have a solution. So n squared, or in this case 1 squared, equals x plus the floor of root x has no solutions. Okay, so that means we're going to start with our n being greater than 1. Okay, fine. So from now on, assume n is greater than 1. Okay, so we're going to try to solve this equation here, n squared equals x plus the floor of root x, where n is greater than 1. And one thing that's going to be really helpful here is to recall that there's a very consistent way that you go from one square to the next. So if I'm at, say, n minus 1 squared, in order to get to n squared, I have to add 2n minus 1. Right? So I'm always going to be adding an odd number, in this case the n minus first odd number, in order to get to the next square. Okay, so what this tells us is that for n greater than 1, this says that, well, actually, first let's write down. This is something which should be very obvious. When n is at least 1, well, n minus 1 is positive, and n minus 1 will be strictly less than 2 times n minus 1, because they differ by n. Okay, but the above equation now is going to tell us that n minus 1 quantity squared is going to be less than n squared minus n minus 1. Okay? We know the difference between them is 2n minus 1, and n minus 1 is less than 2n minus 1. So n minus 1 squared will be less than the difference of n squared with n minus 1. On the other hand, this is certainly strictly less than n squared, because I've gotten rid of something positive, because n was greater than 1. Okay, but now let me take the square root of everything. All right, everything is positive here, so that's not a problem. And I get that n minus 1 is less than the square root of n squared minus n minus 1, and that will be less than n. Okay. But here I have now some number which lies in between n minus 1 and n. And so if I take the floor function of this number in the middle, so if I take the floor function, this tells me, right, it's smaller. This number here is smaller than n, but it's bigger than n minus 1, so the floor will be n minus 1. n minus 1 is the largest integer, which is less than, not even less than or equal, but less than this number in the middle. So the floor of the square root of n squared minus n minus 1 is equal to n minus 1. And so if I take n squared and subtract n minus 1, so that's this number in the middle, and I add to it the floor of the square root of n squared minus n minus 1, notice it's the same number, I get n squared minus n minus 1 plus n minus 1, which is just n squared. And so this right here is what I can treat as my x. And I've solved the equation. For every n at least 1, I've solved this equation. N squared is now x plus the floor of root x. And so all solutions, right? So all possible x are of the form n squared minus n minus 1.